Boom. So we're back again. The next part we're going to discuss. In the former class, we were able to look at acid bases and salts according to Arrhenius, Bronsted and Laurie, and G. N. Lewis, and other like Antoine Lavoisier, Robert Boyce, Davis, definition, Gay-Lussac's, and all that. So in this chapter or this continuation of ABS, we are going to be discussing strength of an acid. Thereafter, we talk about leveling effect and differentiating effect or differentiating solvents. And then we talk about strength of acids in terms of electropositivity, in terms of charge density, in terms of sunk, and thereafter we look at salts. Is that okay? All right, strength of an acid. An acid is said to be very, very strong when it completely ionizes in water, while an acid is said to be very weak when it partially ionizes in water. Strong gases like HCl will ionize to give you hydrogen ion and chloride ion, and their percentage ionization is usually 99 to 100%. Weak acids like ethanoic acid or acetic acid have a ionization percentage of about 0.2 or maybe 2.5. Let me not exaggerate. 0.2 is too low. 2.5%. That means 97.5% of it remains unionized. Then you refer to them as weak acids because of their low level of ionization. And usually you can also recognize that by the presence of a reversible reaction, which will always take place in the direction of the acid itself. So the equilibrium position will always shift towards the acid, and the reason is because the acid will be formed more than the ions. And then it's also important for you to know that the conjugate acid and base coming out from such weak acids are usually strong conjugate acids and strong conjugate bases. So that takes us to the leveling effect. Leveling effect of a solvent is simply the ability of a solvent to limit or to level the strength of an acid or a base that reacts with the solvent. The ability of a solvent to limit or to level the strength of an acid or a base is called leveling effect. Hence, for an acid, the strength of an acid is leveled or limited by the basicity of the solvent, while the strength of a base is leveled or limited by the acidity of the solvent. Water is a very perfect example of a leveling solvent. It can level acids and level bases as well. As for acids, water will level an acid to hydrozonium ion, no matter the strength of the acid. Even the most powerful acid in chemistry will be leveled to hydrozonium ion. And a typical example is antimony hexafluoric acid. It will level it to hydrozonium ion. The weakest acid, which you know as ethanoic acid, will be leveled to hydrozonium ion. So no matter your strength, you'll be brought down to hydrozonium ion in water. And that is why there is a saying that there is no acid that is stronger than hydrozonium ion in water, because hydrozonium ion is the peak. It levels all acids to that level. Hence, water is a perfect leveling solvent. And the same water acts as a perfect leveling solvent for bases, because what it will do, it will reduce all bases to OH minus. No matter the base you are, it will reduce you to OH minus. However, it is also important for you to know that in as much as water acts as a leveling solvent by bringing all acids at the same level, there are other substances that act as differentiating solvent that actually reduce the strength of acids or bases when they come in contact with them. And a perfect example of such substance is ethanoic acid. Did I say ethanoic acid? Yes, ethanoic acid. Ethanoic acid is a very perfect leveling solvent. When we say ethanoic acid is a differentiating solvent, I want to say. Ethanoic acid will react with HCl to give you a strong conjugate acid plus chlorine minus. Ethanoic acid at that point acts as a weak base, and a weak base will produce a strong conjugate acid. And the conjugate acid you're going to have is H3COOH2 all in bracket plus, which is a strong conjugate acid. So it has revealed the strength of the acid in that reaction. The same thing will happen with tetraoxosulfate 6. It will reveal the strength in that reaction. Now, the next we're going to look at how to determine the strength of acid and bases. There are basically three methods I'm going to show you of how to determine the strength of acid and bases. Number one, from their conjugates. Number two, And of course, from that conjugate we're talking about involve the storyline between Clement and Sonia. And then number two, through electronegativity. And then number three, through charge density, okay? Through the charge density. They are very simple ways to recognize. So we start with conjugate through their conjugates. A weak acid has a strong conjugate base, while a weak base has a strong conjugate acid. Now, you have to remember the song between Clement and Sonia because it's key. Clement and Sonia identify bromine. Clement now offers Sonia a place for the night. Eric, Catherine, and Sophia knew cyanide, potassium carbonate, and water. That's the song, a very magnificent song at that. And that will reveal a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 acids in terms of their hierarchy. Clement and Sonia identify bromine. Clement now offers Sonia a place for the night. Eric, Catherine, and Sophia knew cyanide, carbonate, and water. Now, Clement actually is chlorine. The most powerful acid as far as chemistry textbook is concerned is HClO4. That's tetrachloro, right? Now, the next Clement is HCl. Sonia is tetraoxosulfate acid. The next Sonia you're going to hear is HSO4 minus. Now, which you will hear is for nitric acid. The next now will be in the form of nite, and that will be HNO2. And then alpha is hydrozonium ion. Okay, alpha is the hydrozonium ion. And then the place actually is phosphate, right? Triox, that's a tetraoxophosphate 5, as the case may be. And then Eric is to ethanoic acid, Catherine is to carbonic acid, while Sophia is to hydrogen sulfide, ammonium is to new cyanide, carbonate, and water. Carbonate is now the HCO3 minus version of Catherine, right? So you just have to remember that. All right, Clement and Sonia identified is HI, bromine is HF, Clement is HCl, now is ammonia, alpha is to hydrozonium ion, Sonia is to hydrogen tetraoxosulfate 6 minus, and then place is to phosphoric acid. For night, 4 is to hydrofluoric acid, night is to N2, HNO2, Eric is to ethanoic acid, Catherine is to carbonic acid, Sophia is to hydrogen sulfide, new is to ammonium ion, cyanide is to HCN, that's hydrocyanic acid, carbonate is to HCO3 minus, and then water is the last guy there, which is the weakest acid in chemistry, water. Next is to write their conjugates. For you to write their conjugate is very simple. Just remove one of their protons, and that will give you their conjugate. So HClO4 is the strongest acid. However, it is the weakest base. The last guy at the bottom is H2O, which is the weakest acid. However, will give you the strongest base as OH minus. Good, so it will lose a proton. However, there are some substances that will not ionize in water to lose protons. For example, hydrogen cyanide ion, ethanol, that's C2H5OH, hydrogen, methane, those guys will not ionize in water. I can see ammonia here, but there are set situations where ammonia can actually, and that will happen when you have auto-ionization. But let's leave ammonia as an example. So we have hydrogen cyanide, you have ethanol, not ethanoic acid now, hydrogen and methane. Then you can also put ammonia as the case may be. So that is that for conjugate acid. Next, we look at electronegativity. The higher the electronegativity of a substance, the more acidic the substance is. No wonder the most powerful acid in chemistry, which is actually fluoroantimonic acid or hexafluoric acid or hexafluoric antimonic acid, is the most powerful acid with 6 atoms of fluorine. Now take note, hydrofluoric acid is not a strong acid. This is an exception to the rule. The reason is because hydrofluoric acid actually has a very little dissociation value of about less than 2.5%. So it will always form itself than dissociating. So it's a very weak acid. However, in period 3, as you move from carbon, nitrogen, oxygen to fluorine, electronegativity increases and acid forms through these compounds actually have increasing strength in that order, while bases formed through these compounds have decreasing strength in that order. For example, for carbon, you can have methane ion, that is CH3 minus. For nitrogen, NH2 minus. For oxygen, OH minus. And then for fluorine is F minus. So as you move in that direction, basic strength decreases, right? Good. So another property we're going to look at is the guy we call the charge density. Now, as for the charge density, it's a very simple way to identify. It is simply directly proportional to the magnitude, or let me put it this way, this is a very simple language. I don't want to follow the language here. Charge density is directly proportional to the strength of an acid, but inversely proportional to the strength, sorry, did I say acid? I take it again. Charge density is directly proportional to the strength of a base, but inversely proportional to the strength of an acid. That means as the charge density increases, the acid strength decreases. As for a base, as the charge density increases, the acid strength increases, the basic strength increases as well. I'll give you a typical example. I'm just going to use one example to, showcase everything. And the example here is tetraoxophosphate 5. Tetraoxophosphate 5 will undergo 3 steps of dissociation. The first step is H2PO4 minus. The second step is HPO4 2 minus. The last step is PO4 3 minus. Now, if you look at the charge moves from 1, 2, and then 3. Ignore the negative sign, okay? Ignore the negative sign. The charge moves from 1, 2, and then 3. Now, when the charge is 1, the acid strength is maximum. When the charge is 3, the bigger the charge, the lower the strength of the acid. So the acid strength is minimum. But as for the basic strength, as the charge increases from 1 to 3, the basic strength increases from 1 to 3. So what we are saying is that as that number increases, the basic strength increases. As that number increases, the acidic strength decreases. And whenever you see a substance that does not have a charge, it simply means that the charge density is 0. You get it? So ignore the signs and work on the charge density. So basically, that settles the aspect of strength of an acid, and that takes us to the very last chapter. And the last chapter here is salt. And the big question is, what is a salt? What is a salt? What is a salt? A salt is a compound formed when any of the replaceable hydrogen ion on an acid is replaced by an equivalent number of metallic ion. It gives you a salt. There are 5 basic types of salts. We have the normal salt, the acid salt, the basic salt, the double salt, and we have the complex salts, right? Good. We start with the normal salt. Normal salts are formed when the hydrogen ion completely replaces, or let me say, when the hydrogen ion in an acid is completely replaced by a metallic ion. That forms what we call a normal salt. And usually this happens when their concentrations are virtually equal, okay? So you have probably HCl reacting with sodium hydroxide to give you sodium chloride plus water. And then you have acid strength. As I say acid strength, the next one you have is acid salts. Now, as for acid salts, it is formed when there is a partial replacement of the hydrogen ion. And this is usually when there is an insufficient amount of base to completely neutralize the acid. And then you now have the hydrogen lingering into the formula. And this always is usually applicable in dibasic or tribasic acids, okay? A monobasic acid cannot form an acid salt. It's not possible. So, for example, when you have sodium hydroxide reacting with tetraoxosulfate 6 to form sodium hydrogen tetraoxosulfate 6, that's an acid salt. And you can have plenty examples like that. Basic salts. Basic salts are formed when there is an incomplete or insufficient supply of acid for the complete neutralization of the base. And this is usually recognized by the presence of oxygen. Yeah, the presence of oxygen that replaces the hydroxide ion. For example, you have antimony chloride plus water to give you antimony oxychloride plus HCl. So SbOCl is a basic salt. Another example of basic salts are zinc hydroxide or zinc chloride hydroxide, and then you talk about magnesium chloride hydroxide as the case may be. Take note, basic salts turn red litmus paper blue. Yeah, because they are basic. And can react with excess acid to form normal salts. Very important. So if you have a basic salt in the presence of excess acid, it will form a normal salt. And that takes us to double salt. Double salts are salts which ionizes to form three different types of ions. You have two of them which are positive ions, and then one which is a negative ion. The two positive ions, one is made up of a monovalent element, while the other is made up of a trivalent element. As for the negative ion, usually it's a sulfate ion. Usually sulfate. So for the monovalent ions, you can find stuff like potassium, sodium, ammonium. You get it? Then for the trivalent, you talk about iron 3, you talk about chromium, you talk about aluminium. So the perfect formula for a double salt is Y plus dot X3 plus in bracket sulfate with 2 at the bottom dot 12 water. Always 2 at the bottom. Don't bring 2 on the other side of the metallic ion. That's not the right formula, right? So, and this formula is referred to as an alum. It is not called an alum because of the presence of aluminium. No. Alums are alums, irrespective of whether you have aluminium or not. For example, ammonium ferrate tetraoxosulfate 6 dodecahydrate is called ferric alum, right? Then also sodium aluminium tetraoxosulfate 6 dodecahydrate is called soda alum. Potassium aluminium tetraoxosulfate 6 dodecahydrate is called potash alum. Potassium chromate tetraoxosulfate 6 dodecahydrate is called chrome alum. You see, there must not be aluminium to make it an alum. That's the point. And when it comes with 24, it means you have the salts combined in their raw states, like potassium tetraoxosulfate 6, and then you have chromate tetraoxosulfate 6. Then you now have 24. Icosa is to 20, so tetraicosahydrate. You get the point. All right, that takes us to the last point, which is the complex salts. Complex salts is simply a salt that can be formed from complex ions. Example of complex ions are ammonium ion, sulfate ion, triazonitrate ion, right? Now, examples of complex salts are potassium hexacyanoferrate 2, sodium hexacyanoferrate 3, and then you can also have petroamine copper 2 sulfate. That is CuCHNH3 in bracket 4, then sulfate. That's petroamine copper 2 tetraoxosulfate 6, as the case may be. Then you have the potassium argentocyanide, which is KAG in bracket cyanide 2, also called potassium dicyanoargentate. So you can call it potassium argentocyanide or potassium dicyanoargentate. And that is the end of this amazing chapter. And we have finally gotten to the end of acid, bases, and salts. In the next chapter, we are going to look at AB reactions, which is acid and basis reactions. Boom.